Welcome to our channel and this new video. Have you ever wondered why, in the microscopic world, things seem so fundamentally unpredictable? Imagine peering into the world of atoms and particles, only to discover that some aspects of their behavior are forever shrouded in mystery. This isn't just a philosophical reflection, but a fundamental reality of quantum mechanics, summarized in one of its most fascinating principles, Heisenberg's uncertainty principle. At a fundamental level, today we will uncover this concept, explore why it governs particle behavior, and understand why it's not just a peculiarity, but a profound aspect of reality. Imagine you're on a quest to uncover the secrets of a hidden world, one that exists on scales far beyond our daily experience. This world is inhabited by particles, tiny, elusive entities that dance in ways that defy our classical intuitions. In this realm, every action and measurement seems to come with an unavoidable surprise: uncertainty. To begin, let's take a step back and imagine a particle, like an electron, moving within an atom. In classical mechanics, we would expect to be able to measure its position and velocity with great precision. But in quantum mechanics, things aren't so simple. This is where Heisenberg's uncertainty principle comes into play. Werner Heisenberg, a brilliant physicist of the early 20th century, proposed a revolutionary idea. There are fundamental limits to how precisely we can know certain pairs of physical properties of a particle. Specifically, the uncertainty principle states that it is impossible to measure both the position and momentum, which is the product of mass and velocity, of a particle with precision simultaneously. We cannot determine both parameters precisely, because the essence of Heisenberg's principle lies in the intrinsic limits of measurement at the quantum level. Let's delve into this concept. Consider trying to measure the position of an electron with the utmost precision. As you get closer to its exact position, you might think you're gaining more and more information about where it is, but the moment you achieve high precision in measuring its position, the uncertainty about its momentum, that is, its mass and velocity, begins to increase. This isn't due to a flaw in our measuring instruments, but to the nature of quantum particles themselves. In more concrete terms, imagine using a high-resolution microscope to measure a particle's position. The act of illuminating the particle to see it disturbs it. This disturbance makes it harder to measure its momentum precisely, which in turn affects the precision of its position. The more you try to focus on one aspect, the less you know about the other. You might wonder why this uncertainty specifically applies to position and momentum. The answer lies in the mathematical framework of quantum mechanics. In this framework, position and momentum are described as conjugate variables. These pairs of variables are intrinsically linked such that knowing one precisely leads to greater uncertainty in the other. This concept extends beyond position and momentum. For example, energy and time are also conjugate variables. If you try to measure a system's energy with high precision, there will be a corresponding uncertainty in the moment when that energy is measured, and vice versa. This interconnection reflects the deep nature of quantum uncertainty. Although position and momentum are the most commonly discussed pair, the uncertainty principle also applies to other pairs of conjugate variables, such as angular momentum and angle. Imagine a spinning top. Knowing its precise orientation gives limited information about its rotational speed and vice versa. This is another example of how uncertainty operates in quantum systems. An intriguing example of this principle in action is found in the behavior of electrons in atoms. When an electron transitions between energy levels, it emits a photon. According to the uncertainty principle, the more precisely you measure the time when the photon is emitted, the less precisely you can know its energy. This is a direct effect of the principle and highlights its fundamental role in understanding quantum phenomena. At the heart of Heisenberg's uncertainty principle is Planck's constant. This small constant defines the scale of quantum uncertainties and sets the limit to how precisely we can measure pairs of conjugate variables. Planck's constant is like a cosmic ruler that sets the boundaries of how precisely we can know certain pairs of physical properties. For instance, if you measure a particle's position with high precision, the product of the uncertainty in position, dx, and the uncertainty in momentum, dp, cannot be less than 2. This constant effectively quantifies the limit imposed by nature itself. Understanding Heisenberg's uncertainty principle isn't just a theoretical exercise, but has practical implications in technologies such as electron microscopes and quantum computers. Quantum mechanics principles, including uncertainty, play a crucial role. These technologies exploit the peculiarities of quantum behavior to achieve advances that classical physics alone could not. For example, quantum computing relies on the principles of quantum superposition and entanglement, which are deeply connected to the intrinsic uncertainty in quantum measurements. By harnessing these quantum properties, we can develop computing power far exceeding traditional methods. One of the most fascinating aspects of the uncertainty principle is its impact on the nature of measurement itself. In quantum mechanics, the act of measurement fundamentally alters the state of what is being measured. This is a departure from classical physics, where measurements are considered passive observations. In the quantum realm, measurement is one that influences the outcome. This means our attempts to measure a particle's properties are inherently limited by the disturbances we introduce. This intertwining of measurement and uncertainty challenges our classical intuitions about the nature of reality. The uncertainty principle isn't just a quirk of quantum mechanics, but reflects the broader philosophical implications of the quantum world. It suggests that, at a fundamental level, the universe is not deterministic but probabilistic. This has profound implications for our understanding of reality, causality, and the limits of human knowledge. As we delve deeper into the quantum world, we encounter questions that challenge our perception of reality. The uncertainty principle is a reminder that the universe operates on principles that defy our classical expectations, and that our understanding is limited by the fundamental nature of the quantum realm. So, the next time you ponder the mysteries of the microscopic world, or grapple with the implications of quantum mechanics, remember that Heisenberg's uncertainty principle is a cornerstone of our understanding. It encapsulates the essence of quantum uncertainty and challenges us to rethink our notions of measurement and reality. With that said, thank you for joining us on this journey through the fascinating world of quantum mechanics. If you enjoyed it, don't forget to leave a like, subscribe to the channel, and hit the notification bell.